Somewhere over the South Atlantic right now, a satellite is going blind. Not because anything has struck it, not because a system has failed. The spacecraft is functioning exactly as designed, but as it crosses an invisible boundary stretching from Brazil to southern Africa, its operators on the ground send a quiet command. Shut down the most sensitive instruments. Close the eyes. Wait. The Hubble Space Telescope does this. The International Space Station does this. Dozens of satellites in low Earth orbit circling the planet every 90 minutes perform this same ritual several times a day. They enter a region where Earth's magnetic shield, the invisible armor that has protected life on this planet for billions of years, sags inward like a deflating balloon, dipping down to an altitude of roughly 200 kilometers. In that zone, charged particles from the sun that should be held at bay thousands of kilometers overhead instead reach down to brush against anything passing through. The region has a name. Scientists call it the South Atlantic Anomaly, and it is not shrinking. Since 2014, this weak spot has expanded by an area roughly half the size of continental Europe. It drifts westward at about 20 kilometers per year, as if slowly sliding across the face of the planet. In recent years, it has begun to split, developing a second center of minimum intensity southwest of Africa, like a wound that refuses to heal cleanly. The minimum field strength within it has dropped from around 24,000 nanoteslas in 1970 to approximately 22,000 today. These are not numbers that mean much in isolation, but they represent a trend, and the trend is not reversing. Here is the paradox that opens this film. An invisible planetary shield, one most people never think about, can fail locally enough to force modern technology into defensive postures. Yet a survey of over 2,400 videos on related topics finds essentially no sustained account of the larger story. The South Atlantic Anomaly makes the news occasionally, usually framed as a curiosity or a minor technical challenge. What rarely gets explained is what it might represent. Because the question that matters is not whether Earth's magnetic field is changing. It is changing. It has been measured, continuously and precisely, since the 1830s. The question is what kind of change humanity is actually watching. Let that settle for a moment. We're going to spend some time together with this question. Not to answer it, no one can answer it yet, but to understand what it means, where it comes from, and what it would mean if the answer turned out to be the one that keeps a small community of geophysicists awake at night. This is a story written in stone, recorded in the seafloor, preserved in the frozen alignment of iron atoms that locked into place when the world was young. It is a story about a planet that has done something extraordinary, over and over, across hundreds of millions of years, and may be preparing to do it again. If this is the kind of question that pulls you deeper, consider settling in. This will take time. The evidence is patient, and so is the telling. Now let us begin. The South Atlantic Anomaly is not a hole in the sky. That is the first thing to understand, because the phrase gets used loosely, and it creates the wrong picture. The atmosphere is intact. The ozone layer, whatever its own troubles, is not involved here. What has weakened is something deeper and stranger. The magnetic field generated by Earth's liquid outer core, 3,000 kilometers beneath your feet, where iron hotter than the surface of the sun churns in slow convective currents, conducting electricity, generating the invisible force that makes compasses point north. That field extends outward from the planet's interior, wrapping around Earth like the field around a bar magnet, except that Earth is not a bar magnet. The field is generated dynamically, continuously, by the motion of that liquid iron. It is not static. It never has been. And the South Atlantic Anomaly is a place where something about that generation has gone wrong. Not catastrophically wrong, not yet, but measurably, persistently, increasingly wrong. Picture the field as a kind of bubble surrounding the planet. In most places, that bubble holds firm, deflecting the solar wind, the constant stream of charged particles blowing outward from the sun, around and past Earth, channeling it toward the poles where it creates the aurora. But over the South Atlantic, the bubble sags, it dips inward. The inner Van Allen radiation belt, a donut-shaped zone of trapped particles that normally sits comfortably above the atmosphere, descends in this region to altitudes where satellites orbit. The spacecraft passing through encounter radiation levels many times higher than normal. Electronics get hit by particles they were never designed to absorb. Data gets corrupted, sensors malfunction, and so the operators do the only sensible thing. They shut down what they can, ride out the passage, and resume operations on the other side. This has been happening for decades. It is not new. What is new, or at least newly appreciated, is the scale of the change. When systematic monitoring of Earth's magnetic field began in the middle of the 19th century, following the pioneering measurements of Carl Friedrich Gauss in the 1830s, the field was already weaker over the South Atlantic than anywhere else on the planet. But it was weaker by a modest amount. The anomaly existed, but it was a regional curiosity, not a global concern. Since then, the global average field strength has dropped by approximately 9%. That decline is not uniform. Some regions have weakened more than others, and the South Atlantic anomaly has deepened faster than almost anywhere else. 9% may not sound like much, but consider the timescale. 200 years is nothing in geological terms. It is less than the blink of an eye. If the field continued weakening at this rate, and there is no guarantee it will, but also no guarantee it will not, it would reach zero in roughly 2,000 years. That is not a prediction. It is a mathematical extrapolation, the kind of thing scientists are careful to qualify. But it illustrates why the trend matters. Something is happening. Something has been happening since before anyone was measuring it. And the South Atlantic anomaly is the most visible symptom. The astronauts on the International Space Station know this region well. They do not see it exactly. There is nothing to see, but they feel its effects. Radiation monitors spike when the station passes through. Laptop screens sometimes flicker. Occasionally, astronauts report seeing flashes of light with their eyes closed, cosmic rays passing through their retinas and triggering phantom signals. The station's orbit is low enough, and the anomaly's reach is deep enough, that these passages are a regular part of life in space. The crew has adapted, the engineers have adapted, the protocols are in place. But the adaptation is a kind of admission. It says, here is a part of our planet's protective system that no longer works as well as it once did. Here is a weakness in the shield, and the weakness is growing. Rest with that for a moment. Let the scale of it settle. We are not talking about a local phenomenon, some quirk of geology beneath Brazil. We are talking about a feature of Earth's magnetic field that spans an ocean, that affects every satellite passing overhead, that has been expanding and deepening for as long as we have been able to measure it. The question is not whether it exists. The question is what it means. To answer that, or to begin approaching an answer, we need to leave orbit. We need to descend past the atmosphere, past the ocean surface, past the kilometers of water pressing down with unimaginable weight, all the way to the seafloor. Because that is where the record is kept. That is where Earth has been writing its magnetic history for hundreds of millions of years in a medium that does not forget. The ocean floor is not what most people imagine. It is not sand. It is not mud, mostly. In the deep basins, far from the continents, the floor is basalt, black volcanic rock, erupted from the mantle, cooled by seawater, and spread outward from the mid-ocean ridges like a slow-motion conveyor belt. This rock is young, geologically speaking. The oldest oceanic crust is only about 200 million years old, because anything older has been subducted back into the mantle at the edges of tectonic plates. But 200 million years is more than enough to contain a remarkable archive. The key is iron. Basalt contains iron-bearing minerals, primarily magnetite. When the rock is molten, erupting from the ridge in superheated plumes, these minerals have no fixed magnetic orientation. They are too hot. Their internal structure is disordered, randomized by thermal energy. But as the lava cools, and it cools quickly in contact with near-freezing seawater, something happens. At a specific temperature, around 585 degrees Celsius, the minerals pass through what is called the Curie point. Below that temperature, the iron atoms in the magnetite crystals can hold a permanent magnetic alignment, and they align with whatever magnetic field surrounds them at that moment. In other words, they align with Earth's magnetic field. This is not a subtle effect. It is not a faint trace that requires sophisticated instruments to detect. The magnetization is strong enough that you can tow a magnetometer behind a ship, dragging it through the water above the seafloor, and measure the magnetic field of the rocks below. This is exactly what researchers began doing in the years after World War II, when the technology developed for submarine detection was repurposed for scientific exploration. And what they found changed everything. The seafloor is striped. Not visibly. The rock looks the same everywhere, black basalt covered in sediment. But magnetically, the floor is divided into alternating bands of normal and reversed polarity. In some bands, the iron minerals point toward magnetic north, just as a compass needle does today. In others, they point south. The bands run parallel to the mid-ocean ridges, and they are symmetric. The pattern on one side of a ridge mirrors the pattern on the other. Let me put that in perspective. Imagine standing at the crest of the Mid-Atlantic Ridge, the underwater mountain range that runs down the center of the Atlantic Ocean like a spine. If you could see magnetic polarity the way you see color, you would see stripes extending away from you in both directions, alternating dark and light, matching each other like the two halves of a Rorschach test. The stripe directly beneath your feet would be magnetized in the current direction, normal polarity pointing north. The next stripe out on both sides would be reversed. The one after that, normal again, and so on for thousands of kilometers, all the way to the continental margins. This pattern is not random, it is a record. Each stripe represents a period when Earth's magnetic field held a particular orientation, north pointing north or north pointing south, and the rocks that formed during that period preserved that orientation forever. The stripes are a timeline, a magnetic tape recording of planetary history, written in stone and readable from a ship. The first people to fully understand what they were looking at were a small group of geophysicists working in the early 1960s. Frederick Vine was a graduate student at Cambridge. Drummond Matthews was his supervisor. Independently, on the other side of the Atlantic, a Canadian geophysicist named Lawrence Morley was reaching the same conclusions. What they proposed was elegant and revolutionary. The stripes were created by seafloor spreading. At the mid-ocean ridges, new crust is constantly being created. Magma rises from the mantle, erupts onto the seafloor, cools and solidifies. As it cools, it locks in the current magnetic field direction. Then more magma rises behind it, pushing the older rock outward, away from the ridge. The process is slow, a few centimeters per year, roughly the speed at which your fingernails grow, but it is relentless. Over millions of years, it creates new ocean floor and pushes the continents apart, and every time the magnetic field reverses, the newly forming rock records that reversal. The old rock, already cooled and magnetized, keeps its original orientation, but the new rock takes on the opposite polarity. The result is stripes, alternating bands of normal and reversed magnetization, spreading outward from the ridge like tree rings spreading outward from the center of a trunk. Vine and Matthews published their hypothesis in the journal Nature in September 1963. The paper was short, only 3 pages, but its implications were vast. It provided the first physical mechanism for continental drift, the idea that the continents move across Earth's surface over geological time. That idea had been proposed decades earlier by Alfred Wegener, but it had been dismissed by most geologists because no one could explain how continents could possibly move through solid rock. The seafloor spreading hypothesis answered that question. The continents were not ploughing through the ocean floor, they were riding on it, carried along by the slow conveyor belt of newly created crust. But the hypothesis also revealed something else, something that would have seemed impossible to earlier generations of scientists. Earth's magnetic field had reversed, not once, not twice, hundreds of times. The stripes on the seafloor were a record of those reversals, stretching back as far as the oldest oceanic crust could preserve. The last full reversal, the most recent time that north became south and south became north, occurred approximately 780,000 years ago. It is called the Brunhes-Matuyama reversal, named for the scientists who first identified the magnetic epochs on either side of it. Before that reversal, compasses would have pointed south. After it, they point north. We are living in the Brunhes normal epoch, and we have been for the better part of 1 million years. But 780,000 years is not a long time by the standards of this record. The stripes show that reversals have happened irregularly throughout Earth's history, sometimes separated by millions of years, sometimes by only tens of thousands. There is no clock. There is no schedule. The field reverses when it reverses, driven by processes in the outer core that we are only beginning to understand. And here is the part that connects back to where we started. The field does not simply flip like a switch. Before a reversal, the field weakens. It becomes unstable. It develops anomalies, regions where the field is unusually weak or where the local field direction deviates from the global pattern. The South Atlantic Anomaly is exactly the kind of feature you might expect to see in a field that is preparing to change. That does not mean a reversal is imminent. The current weakening could reverse itself. The anomaly could stabilize or shrink or migrate to a different location. Scientists who study the paleomagnetic record emphasize that similar anomalies have appeared before and resolved without leading to a full reversal. A 2022 study published in the Proceedings of the National Academy of Sciences identified ancient analogues for the current South Atlantic anomaly, suggesting it may be a recurring temporary phenomenon rather than a terminal collapse. But the honest answer is that no one knows. We have been measuring the field precisely for less than 2 centuries. The geological record shows us what happened in the past, but it cannot tell us what will happen next. We are watching a process unfold on a timescale that dwarfs human civilization, and we are trying to read its trajectory from a single snapshot. Let that settle for a moment. The story of how we came to understand any of this, the stripes, the reversals, the spreading seafloor, is itself a story worth telling, because it was not obvious. It was not handed down from theory. It was assembled piece by people who were willing to look at evidence that contradicted everything they had been taught, and to follow that evidence wherever it led. Marie Tharp was one of those people. In the 1950s, she was a geologist and cartographer working at Columbia University's Lamont Geological Observatory, and she was doing something that no one had done before, mapping the floor of the Atlantic Ocean. Not from a ship. Women were not allowed on research vessels at the time, but from the data that ships brought back. Sonar readings, depth soundings, thousands upon thousands of measurements, taken along crisscrossing ship tracks, each one a single point in a vast 3-dimensional puzzle. Tharp took those points and turned them into maps. She worked with a geologist named Bruce Heason, who led many of the research cruises that gathered the data. Together, over years of painstaking work, they produced the first detailed images of the Atlantic seafloor. And what those images showed was unexpected. There was a ridge running down the centre of the Atlantic. That much had been suspected. But the ridge was not a simple underwater mountain range. It had a valley running along its crest, a rift valley, a deep cleft splitting the ridge down the middle, as if the seafloor were being pulled apart. Tharp recognized the significance immediately. A rift valley meant extension. It meant the crust was spreading, opening up, making room for new material to rise from below. When she showed the maps to Heason, he was skeptical. The idea of seafloor spreading was too close to continental drift, which was still considered fringe science by most geologists. He reportedly dismissed her interpretation as girl talk, but the data kept coming in, and the rift valley kept appearing, not just in the Atlantic but in every ocean basin they mapped. By 1957, Tharp, Heason, and their colleague Maurice Ewing had produced a physiographic map of the Atlantic seafloor that showed the mid-ocean ridge system in stunning detail. The evidence was becoming impossible to ignore. The magnetic stripes came next. As magnetometer surveys accumulated through the late 1950s and early 1960s, the pattern became clear. Symmetric bands of alternating polarity, centered on the ridges, extending outward toward the continents. Vine and Matthews provided the explanation. Morley, working independently, reached the same conclusion but had trouble getting his paper published. One reviewer reportedly called it too speculative. The history of science is full of such ironies. By the mid-1960s, the revolution was complete. Continental drift, rebranded as plate tectonics, became the unifying theory of Earth science. The magnetic stripes were its Rosetta Stone, the key that unlocked the history of the ocean basins and proved that the Earth's surface is in constant slow motion. And embedded in those stripes was another revelation, the record of magnetic reversals, stretching back hundreds of millions of years, written in iron and basalt and preserved beneath miles of seawater. The stripes are still there. New ones are being created right now, at ridges around the world, as magma rises and cools and locks in the current field direction. The process has not stopped. It will not stop until the mantle itself goes cold, billions of years from now. And when geophysicists look at those stripes today, they see not just a record of the past, but a context for the present. Because the field has reversed before, many times, and each time before the reversal the field weakened. It developed anomalies. It became unstable. Sound familiar? The South Atlantic Anomaly is not proof that a reversal is coming, but it is consistent with the early stages of one. The 9% decline in global field strength over the past 2 centuries is not proof either. The field has fluctuated before, and it could recover. but it is consistent with a pattern that has preceded reversals in the past. We are watching something. We do not yet know what. The stripes on the seafloor tell us that this planet has done something extraordinary, over and over, across the span of geological time. The field has collapsed and rebuilt itself. North has become south, and south has become north, and life has continued. The record is clear on that point. Reversals are not extinction events. They are not catastrophes in the sense that an asteroid impact is a catastrophe, but they are not nothing either. What would it mean to live through one? What would it mean for a civilization built under a compass that has always pointed the same direction, protected by a shield that has always held? These are questions that the stripes cannot answer. They tell us what happened. They do not tell us what it felt like, or what it cost, or what was lost, but they tell us that it happened. That is the first thing. That is the foundation on which everything else is built. The reversals are not speculation. They are not apocalypse lore. They are written into the crust of the Earth, on a global scale, in a medium that does not lie. And the South Atlantic Anomaly is a reminder that the process is not finished. The field is not static. It never has been. The shield that protects us is not a wall. It is a living thing, generated fresh every moment by the churning of iron in the deep Earth, and it can change. It is changing now. The last time magnetic north and south exchanged places was 780,000 years ago, give or take a few millennia. The measurement is not precise to the century, or even to the 10,000-year mark, because the rock record blurs at that resolution. But it is precise enough to say that no human being has ever lived through a full geomagnetic reversal. No civilization has, no written language, no agriculture, no city has existed under a sky where the compass needle swung slowly south, and then, over generations, settled there. We have only ever known one magnetic world, the one we are in now. That world has a name. Geophysicists call it the Brunus Chron, the current interval of normal polarity, the span of time during which magnetic north has pointed roughly toward the geographic North Pole and south toward the geographic South Pole. It began 780,000 years ago, at the end of the transition we now call the Brunus-Matuyama reversal, and it has held ever since. Before that, the field was reversed. North was south, south was north. For nearly 1 million years prior, the planet's magnetic field pointed the opposite direction, and the compasses we build today, if they had existed then, would have been wrong, not broken, wrong. Pointing faithfully toward a magnetic south pole located near the geographic north. The Matuyama Chron, the reversed interval that preceded ours, lasted from roughly 2.5 million years ago until the Brunus-Matuyama boundary. Before that, normal polarity again. Before that, reversed. The names pile up as you go backward through geological time. Gauss, Gilbert, deeper intervals with no names, only numbers and polarity labels in the stratigraphic charts. The record goes back hundreds of millions of years. The pattern is irregular but relentless. The field flips, holds for a span of time that might be 50,000 years or might be 1 million, then flips again. There is no periodicity, no clockwork, only the fact of reversal itself, repeated, inscribed in stone, and undeniable. The boundary between the Brunis and Matuyama Chrons is now a formal marker in geological time. In 2020, the International Union of Geological Sciences ratified the Chiba section in Japan as the global boundary stratotype section and point, the physical location on Earth that defines the base of the Shibanian stage and the Middle Pleistocene. A layer of sediment in a riverbank in Chiba Prefecture, containing a record of the reversal transition, is now the reference standard for a slice of Earth's history. It is the kind of quiet scientific milestone that carries enormous weight. A riverbank in Japan is the place where, in stone and magnetized grains, the last full reversal is most clearly written. Pilgrims of a certain kind go there now. But what does reversal mean, in practical terms? It means the field does not vanish and then reappear, pointing the other direction. It means the field weakens, becomes chaotic, and reorganizes. The dipole, the simple bar magnet structure that dominates the field today, deteriorates. Multiple poles appear. The field becomes multipolar, a tangled mess of competing magnetic regions scattered across the surface of the planet. The strength drops, in some estimates to 10% or less of normal levels. The transition is not instant. It unfolds over thousands of years, and while that is a blink in geological terms, it is an eternity in human ones, 100 generations more or less. Long enough that no single person would witness the beginning and the end. Long enough that the memory of what the field used to be like would fade into legend, then myth, then nothing. And then, eventually the field settles. One polarity wins. The dipole re-establishes itself, the strength climbs back toward normal, and the planet has a magnetic field again, just pointing the other way. The geographic poles do not move. That is critical to understand. When we say the magnetic field reverses, we do not mean the Earth flips over in space, or that the rotation axis tilts, or that the continents suddenly find themselves under a different sun. The magnetic reversal is entirely a property of the geodynamo, the engine of molten iron convecting in the outer core, and it has no direct connection to the planet's rotation or its orbit. North remains north, in the geographic sense. The stars do not change. What changes is the invisible field threading through the atmosphere and the rocks in your body, the field that orients migrating birds and magnetotactic bacteria, and every compass needle ever forged. That field reorganizes itself. It chooses, for reasons we still do not fully understand, to point the other way. And it has done this hundreds of times. The seafloor stripes record more than 150 reversals in the past 70 million years alone. Go back further, into the Mesozoic, the Paleozoic, and the count climbs into the hundreds. Some reversals are brief, short-lived excursions where the field starts to flip, weakens dramatically, then snaps back to its original polarity. Others complete the transition and hold for hundreds of thousands of years before flipping again. The Brunner's Chron, our current interval, is neither particularly short nor particularly long by the standards of the record. It is simply where we are, the polarity we were born into, the only one we know. Think about what that means. Every human migration, every civilization, every technological leap from fire to flight to space travel has occurred under a magnetic field pointing in this direction. The Vikings navigated by lodestone. The age of exploration was built on the compass. The map projections that divided the world into hemispheres and trade routes assumed a consistent magnetic north. Even today, aviation, shipping, satellite navigation, power grids, all of it calibrated to the field as it is now, or as it was a few decades ago when the systems were built. We have never had to ask the question, what happens when the compass is wrong? Not because of a local variation, which we understand and correct for, but because the field itself has chosen a new direction. And yet the field has chosen a new direction, many times, long before we were here to notice. The Bruners-Matuyama reversal happened while our ancestors were still early members of the genus Homo, scattered across Africa and beginning to spread into Eurasia. Anatomically, modern humans would not appear for another 600,000 years. There were no cities, no agriculture, no written language to record the slow migration of the auroras toward the equator, or the confusion of whatever animal navigation systems depended on the field, or the increased radiation reaching the surface as the field weakened. The reversal happened and life continued, and we inherited a planet with the field already settled into the polarity we now call normal. But it is not normal in any permanent sense. It is simply current, temporary. One phase in a cycle that operates on timescales so long they make human history look like a flicker. 780,000 years is a long time. Long enough for entire species to evolve and go extinct. Long enough for ice ages to come and go, for coastlines to rise and fall, for forests to become deserts and deserts to become forests. Long enough that if you tried to walk backward through that span, 1 year at a time, you would walk for longer than all of recorded history and then longer than that again, hundreds of times over, and still not reach the point where the field last completed its flip. The Brunner's Chron is old, but it is not permanent, and the stripes on the seafloor, and the sediments in Japan, and the lava flows on every continent all tell the same story. The field does not stay in one polarity forever. It changes, and there is no reason to think it will not change again. The question is not whether it will reverse. The question is when, and whether the current changes, the 9% decline, the South Atlantic Anomaly, the drift of the North Magnetic Pole, the emergence of secondary minima, are the early signs of the next transition, or simply fluctuations within a stable chron. The data do not yet give us an answer. They give us a pattern, a context, and a reminder that the field we live under is not fixed. It is not guaranteed. It is the product of a process happening now, 3,000 kilometers beneath your feet, in a place no human will ever visit, and that process has a history of profound reorganization. Let us go there then. Not physically. No drill bit will ever reach the outer core, no instrument will ever be lowered into the convecting iron, but conceptually. Let us descend through the mantle, past the crust in the rigid lithosphere, through the yielding asthenosphere and the deep mantle's slow convection, down to the core mantle boundary 2,890 kilometers below the surface. There the mantle ends and the outer core begins. The temperature jumps, the pressure becomes crushing. The material changes from solid silicate rock, deformable over geological time but still fundamentally rigid, to liquid metal, iron alloyed with nickel and lighter elements, sulfur perhaps, oxygen perhaps, silicon. The exact composition is still debated, but the state is not. The outer core is liquid. We know this because seismic shear waves, the S-waves generated by earthquakes, cannot pass through it. They require a solid medium to propagate. When an earthquake on one side of the planet sends out seismic energy, the S-waves vanish at the core mantle boundary and reappear on the other side only after travelling through the solid inner core or being converted to other wave types. The shadow they leave behind is the shadow of a liquid layer, 2,260 kilometers thick, wrapping around the solid inner core like the white around the yolk of an egg. That liquid layer is the engine, the geodynamo, the source of the magnetic field. It is not a passive reservoir, it is in constant motion, driven by heat escaping from the core into the mantle, by the slow crystallization of iron onto the inner core as the planet cools, by the release of lighter elements that rise buoyantly through the outer core, by the rotation of the Earth itself. The motion is convective. Hotter, less dense metal rises, cooler metal sinks, but it is also twisted by the Coriolis force, the same force that organizes hurricanes and ocean currents on the surface. In the outer core, the Coriolis force organizes the convection into columnar structures, aligned roughly with the rotation axis, spiraling flows that stretch from the core mantle boundary down to the inner core boundary and back. These flows carry electric currents. The iron alloy is an excellent conductor, and the motion of the conducting fluid through the existing magnetic field generates new electric currents, which generate a new magnetic field, which twist the flow, which generates more current. It is a self-sustaining loop, a dynamo. We cannot see it. We cannot measure it directly. Everything we know about the outer core comes from inference. Seismic waves tell us it is liquid, and they tell us how fast those waves travel, which constrains the density and elasticity. Laboratory experiments tell us how iron behaves under the extreme pressures and temperatures of the core. Experiments using diamond anvil cells and laser heating to replicate conditions that no furnace can reach. Computational models take those constraints and try to simulate the dynamo, solving the equations of magnetohydrodynamics on supercomputers, watching virtual flows organize themselves into virtual magnetic fields, and checking whether the results look like the field we measure at the surface. The models have become remarkably good. They reproduce the dipole structure. They reproduce the drift of the magnetic poles. Some of them even reproduce reversals, spontaneous reorganizations of the field, where the dipole collapses and rebuilds itself pointing the other direction, and nobody told the simulation to do that. It emerged from the physics. But the models are not the core. They are approximations, necessarily simplified, running at resolutions that smooth over the turbulence and the fine structure. The real outer core is vastly more complex. The flows are three-dimensional, time-varying and chaotic in the technical sense, sensitive to tiny changes in initial conditions, unpredictable beyond a certain horizon. And the boundary conditions matter. The core mantle boundary is not smooth. It is sculpted by the mantle above it, by the large low-shear velocity provinces, the mysterious dense structures lurking at the base of the mantle beneath Africa and the Pacific. Those structures affect the heat flow out of the core. They create hot spots and cold spots. They influence the convection, and the convection, in turn, generates the field. Everything is coupled. The mantle affects the core generates the field shields the atmosphere from the solar wind. The solar wind, over geological time, can strip atmospheres from planets that lack a magnetic shield. Mars lost most of its atmosphere that way, after its dynamo shut down billions of years ago. Venus never had a dynamo or lost it early, and its surface is a baked wasteland despite being roughly Earth's size. Earth's magnetic field is not just a curiosity. It is, in a very real sense, part of the reason the surface of this planet is habitable. and that field is generated by a process we can model but cannot observe in a place we can never visit, governed by physics we are still working out. The geodynamo is one of the great remaining problems in Earth science. We understand it well enough to explain its existence. We do not understand it well enough to predict its behavior. We cannot say, with confidence, whether the current changes are part of a normal fluctuation or the beginning of a reversal. We cannot say how long a reversal takes because the estimates vary wildly depending on which rocks you look at and how you interpret the data. Some studies suggest a few thousand years, others suggest tens of thousands. The most recent detailed work on lava flows from the last reversal suggests the transition took at least 22,000 years, but even that is contested. The rock record is noisy. The field during a reversal is chaotic. The signal is hard to read. So we watch. We take measurements. Observatories scattered across the globe, some of them running continuously for more than a century, track the field's direction and strength at fixed locations. Satellites in low Earth orbit, like the European Space Agency's Swarm constellation, measure the field globally, mapping its structure in 3 dimensions, watching the South Atlantic Anomaly evolve in real time, tracking the drift of the magnetic poles year by year. Ground-based instruments and satellites feed data into models, and the models try to reproduce what the core is doing right now. They try to forecast what it will do next year, next decade. The forecasts are not very good beyond a few years, because the system is turbulent and the data are sparse, but they are improving, slowly, carefully, and the scientists running those models, looking at that data, know that they are watching something rare. Not unprecedented, reversals are common on geological timescales, but rare on human timescales, rare enough that we have no historical memory of one. No oral tradition passed down from the last reversal, because there were no humans capable of passing it down. We are, potentially, the first technological civilization to face the possibility of living through a geomagnetic reversal. The first to have satellites that would be affected. The first to have power grids and GPS and communication networks that depend, in subtle but critical ways, on the field being roughly what it is now. The first to have the instruments to watch it happen, and the first to have the knowledge to understand what we are seeing, even if we cannot predict what comes next. The field has weakened before. It has developed anomalies before. The 2022 study in PNAS found evidence of ancient South Atlantic anomalies in sediment cores, moments in the geological record where the field above the southern Atlantic was weak and the anomaly was strong, and those moments were not associated with reversals. Sometimes the field just fluctuates. Sometimes the South Atlantic Anomaly is just the South Atlantic Anomaly, a regional feature that comes and goes, and the global field remains stable. But sometimes it is not. Sometimes the anomaly is part of a pattern, a symptom, an early stage of a much larger reorganization. We do not know which we are seeing now. That uncertainty is uncomfortable. It does not fit neatly into the narratives we tell ourselves about understanding the world, about having the answers, about science giving us certainty. But the uncertainty is real. It is honest. The field is changing, that much is clear. Where it is going, and how long it will take to get there, are questions the Earth has not yet answered. The engine beneath our feet is too deep, too complex, too turbulent to yield its secrets easily. We watch its output. We infer its state. We build models and test them against the data, and we wait. Not passively. There is work to be done, measurements to take, physics to unravel, but patiently. The core moves on timescales that do not care about budgets or publication cycles or human lifetimes. It will do what it does. Our job is to pay attention. The basalt stripes on the ocean floor tell one story. The story of reversals that completed, north switching to south, the polarity locking in, staying put for hundreds of thousands of years before flipping back. But the Earth's magnetic archive is deeper than mid-ocean ridges, and the story it contains is stranger than a simple binary of north and south. Volcanic rocks on land hold the same record. Every lava flow that cools, every ash layer that settles, every volcanic bomb that lands hot and solidifies in place, each one captures the direction and intensity of the field at the moment it crossed below the Curie point. 585 degrees Celsius for magnetite. Below that temperature, the magnetic domains freeze. The field's fingerprint is locked in, and so geologists have been collecting those fingerprints for decades, drilling cores from volcanic sequences in Iceland, in Hawaii, in the Canary Islands, building timelines from stacked layers of eruptions, dating them with radiocarbon and argon-argon methods, measuring the remnant magnetization grain by grain. The volcanic record extends further back than the seafloor, because the seafloor is young. The oldest ocean crust is less than 200 million years old, consumed at subduction zones, recycled into the mantle. But volcanic provinces on continents can be far older, and the rocks, if they are not weathered or reheated, remember. Deep-sea sediments remember too. Fine clays and silts settling to the ocean floor, grain by grain, year after year, accumulating in continuous layers that can span millions of years. Each particle falling through the water column carries a tiny magnetic moment, and as it lands on the seabed, it aligns, weakly, with the ambient field. The alignment is not as strong as in volcanic rock. Sedimentary remnants is a gentler, noisier signal, but it is there. And where sedimentation is steady and undisturbed, the cores pulled from the deep ocean floor give a continuous record of the field's direction and intensity, smoothed by the slow rain of particles but reliable in the aggregate. The sediment cores are how we see the full structure of a reversal, the slow weakening, the directional chaos, the eventual stabilization in the opposite polarity. They fill in the gaps between lava flows. They show the transitions. Ice cores remember, though more indirectly. Cosmogenic isotopes, beryllium-10, carbon-14, produced when cosmic rays strike the upper atmosphere. When the magnetic field is strong, it deflects more cosmic rays away from Earth. When the field weakens, more cosmic rays get through, more isotopes are produced, more beryllium-10 falls with the snow and is buried in the ice. The ice cores from Greenland and Antarctica, stretching back nearly 1 million years in some places, carry a record of cosmic ray flux, and that flux is a mirror of the field's strength. An indirect mirror, noisy, dependent on other factors, solar activity, atmospheric chemistry, but when cross-checked against volcanic and sediment records, it holds. And when you assemble all those archives together, basalt, lava, sediment, ice, you see not just the long reversals but something else, something more unsettling, short-lived events, moments when the field weakened dramatically, when the magnetic poles wandered far from the geographic poles, when the field's direction became chaotic, unstable, multipolar, and then, instead of completing the flip, instead of locking into a reversed polarity, the field recovered. It strengthened again. The poles returned roughly to where they had been. North remained north. South remained south. These events are called geomagnetic excursions, and they happen far more often than full reversals. The Lachaume excursion is the clearest example. Dated to roughly 41,000 years ago, it appears in volcanic records from multiple continents, and in sediment cores from the Atlantic and Pacific. The field weakened to perhaps 5 to 10% of its current strength. The magnetic poles drifted wildly. In some locations, compasses would have pointed south instead of north, at least for a while. The virtual geomagnetic pole, the point on Earth's surface where a simple dipole field would emerge, calculated from any given location's magnetic measurements, moved more than 45 degrees away from the geographic pole. In the formal definition used by paleomagnetists, that crossing of the 40-degree threshold is what distinguishes an excursion from ordinary secular variation. The field was not behaving normally. It was not a brief wobble. It was a near reversal. The most intense phase of the Lachaume's excursion lasted about 300 years. The total duration of field disruption, from the first detectable weakening to the final recovery, was closer to 2,000 years, and then it ended. The field came back. The dipole reasserted itself. The poles stabilized. The Earth's magnetic shield strengthened again, and the excursion became a footnote in the geological record, invisible to anyone not drilling cores or measuring remnants in ancient lava. Humans lived through it. Anatomically modern humans, Neanderthals in Europe, Denisovans in Asia, all of them were alive during the Lachaume's event. There is no evidence in the archaeological record of mass die-offs tied to that moment, no clear signal of catastrophe, though that does not mean there was no effect. A weakened magnetic field means higher cosmic ray flux, higher production of cosmogenic isotopes, more radiation reaching the surface, especially at high latitudes where the field lines converge, more radiation reaching the upper atmosphere, affecting ozone chemistry, potentially altering climate in ways that are still poorly understood. Some researchers have speculated, carefully, tentatively, that the Lachaume excursion coincides with a period of rapid environmental change in Europe, a a cold snap, shifts in vegetation, the final decline of Neanderthal populations. The timing is suggestive, the causality is unproven, correlation is not mechanism, but the fact remains, the field collapsed to a fraction of its normal strength and life continued. That is one excursion. There are others. The Mono Lake excursion, 34,000 years ago. The Blake event, around 120,000 years ago, captured in sediment cores from the Caribbean. The Iceland Basin excursion, recorded in North Atlantic sediments, approximately 185,000 years ago. Some are well dated and appear in multiple independent archives. Others are seen in only one or two locations and may be regional rather than global. Artifacts of the chaotic multipolar field structure that can emerge when the dipole weakens. Defining an excursion turns out to be surprisingly hard. How far must the poles wander? How long must the field stay weak? If the anomaly is only visible in one hemisphere, does it count? The definitions are still debated, but the pattern is clear. Earth's magnetic field does not only reverse, it also falters, it stumbles, and sometimes it catches itself before falling all the way. The question, then, is whether we are seeing one of those stumbles now. Whether the 9% decline since the 1830s, the growth of the South Atlantic Anomaly, the accelerating drift of the magnetic North Pole, whether all of that is the beginning of an excursion, or the beginning of a full reversal, or just noise within the normal range of a chaotic system. The answer is, we do not know. The archives tell us that excursions happen. They do not tell us how to predict one. So we turn to the archive of direct measurement. Not rocks that remember the field as it was thousands or millions of years ago, but instruments that measure the field as it is, right now, and that have been measuring it continuously in some places for nearly 2 centuries. The era of quantitative measurement begins with Carl Friedrich Gauss. Mathematician, astronomer, physicist, one of those 19th century minds that seemed to touch every corner of science. In 1832, Gauss established a magnetic observatory in Göttingen, Germany, working with Wilhelm Weber, his assistant and collaborator. They built instruments capable of absolute measurements of magnetic field strength, not just relative changes. A suspended magnet, carefully shielded, allowed to swing in response to the Earth's field, its motion timed, its period recorded. From that period, and the geometry of the magnet, you could calculate the field's intensity. It was painstaking work. The instruments were sensitive to vibration, to temperature, to the iron nails in nearby buildings. But the measurements were real. They could be compared across time, across continents. They were not dependent on any particular reference standard. They were absolute. Gauss did more than measure. He developed the mathematical framework for describing the field, spherical harmonics, a way of decomposing the field into components, separating the dipole from the quadrupole from the higher order terms, separating the internal field generated by the core from the external fields generated by currents in the ionosphere and magnetosphere. He published the first global magnetic model in 1839. It was crude by modern standards based on measurements from only a few dozen locations, but it was a model. It showed that the field could be described mathematically, that its structure could be predicted, that science could grasp it. Other scientists followed. The 1830s saw a wave of magnetic enthusiasm, sometimes called the Magnetic Crusade, driven by figures like Edward Sabine, who pushed for a global network of magnetic observatories. The goal was to understand not just the field's average state, but its variations, daily swings driven by solar heating of the ionosphere, disturbances during geomagnetic storms, when the solar wind slammed into the magnetosphere and injected currents that lit up auroras and disrupted telegraph lines. Slow, long-term changes, secular variation, that could not be explained by anything happening in the atmosphere or the ionosphere. Those changes, Gauss realized, had to be coming from the core, from something moving, shifting, deep inside the Earth, and the measurements showed something else. The field was not constant, it was declining. Not everywhere. Some regions showed increases, others decreases, but the global dipole moment, the overall strength of the field's dominant component, was dropping. By the late 19th century, enough observatories had been running long enough to confirm the trend. The rate of decline was small, a fraction of a percent per decade, but it was measurable, and it was sustained. Observatories kept running: Göttingen, Greenwich, Bombay, Toronto, Tucson, Hermanus in South Africa, established in 1941 to fill a gap in the southern hemisphere. Instruments evolved, flux gate magnetometers, proton precession magnetometers, cesium vapor sensors, each generation more precise, more stable, less vulnerable to drift. By the mid-20th century, the global network could track the field's changes year by year, and by the late 20th century, those changes were being fed into models. The World Magnetic Model is one of those models, developed jointly by the United States National Centers for Environmental Information and the British Geological Survey. It is the standard used by navigation systems worldwide. Every GPS receiver, every smartphone compass app, every aircraft autopilot, every military targeting system, all of them rely on the World Magnetic Model to convert between magnetic north and true north. The model is updated every 5 years because the field changes too fast for a single model to stay accurate longer than that. The magnetic north pole drifts. The declination, the angle between magnetic north and geographic north, shifts. The South Atlantic Anomaly grows, drifts west, splits into 2 minima. The model has to keep up. The most recent version, released in December 2024, is called WMM 2025. It will remain valid until the end of 2029. After that, a new model will be needed because by then the field will have changed enough that the old one no longer matches reality. This is not a failure of the model. This is the nature of the system. The core is not static. The geodynamo is always shifting, and the field it produces shifts with it. The decline that Gauss and his successors measured has continued. The best estimate, based on observatories and satellite data and historical ship logs, is that the global dipole moment has decreased by about 9% since the 1830s. Some of that decline is concentrated in the South Atlantic. Some is distributed more evenly. The axial dipole, the part of the field aligned with Earth's rotation axis, the part that makes compasses point roughly north, is the component weakening most consistently. The non-dipole components, the regional lumps and dips and twists, are not weakening uniformly. Some are growing. The field is not fading evenly, it is reshaping. Does that mean a reversal is starting? The scientists who study this, geomagnetists, paleomagnetists, geodynamicists, are careful with their language. They say, the field is changing. They say, we are in a period of relatively rapid secular variation. They say, the current rate of decline, if sustained, would bring the dipole moment to zero in roughly 1500 years, but there is no reason to assume the rate will be sustained, because the field has strengthened and weakened before without reversing. They say, we need more data, more time, better models. They do not say a reversal is imminent, because they do not know, and they are honest about that. But the operational community does not have the luxury of waiting for certainty. Satellites are flying through the South Atlantic Anomaly right now. The International Space Station passes through it roughly 5 times a day. Every pass exposes the crew and the hardware to elevated radiation. Energetic protons from the inner Van Allen belt, normally held hundreds of kilometers higher, dip down to altitudes where spacecraft live. 200 kilometers above the surface in the heart of the anomaly, sometimes lower. The flux is high enough to cause single-event upsets, bit flips, where a charged particle strikes a transistor and changes a 0 to a 1 or a 1 to a 0. Most of the time that does not matter. The error is caught, corrected, logged. But sometimes it matters. Sometimes the flipped bit is in a critical register and the instrument glitches, or a computer reboots, or data are lost. The Hubble Space Telescope shuts down its science instruments every time it crosses the anomaly. Not every pass. Hubble's orbit does not always take it through the densest part, but often enough that the shutdown protocols are routine. The instruments are powered off. The telescope goes into a safe mode. It waits until it is clear of the anomaly, then powers back up and resumes observations. This is not an emergency procedure. This is normal operations. The anomaly is part of the environment now. You plan for it. You work around it. Other satellites do the same. Earth observation missions, communication satellites, anything in low Earth orbit with sensitive electronics. They all have anomaly crossing protocols. Some shut down, some switch to redundant systems, some just log the increased error rates and accept the risk. The risk is not zero, but it is manageable. So far. The anomaly has been growing since at least the 1970s, when satellites first began measuring it consistently. The minimum field strength within the anomaly has dropped from roughly 24,000 nanoteslars in 1970 to about 22,000 today. The area has expanded. The western edge has drifted across the South Atlantic, approaching the coast of South America. A second minimum has formed southwest of Africa, weakening further, and some researchers think the anomaly is splitting into two distinct cells. That splitting, if it continues, could be significant. A single weak spot is a nuisance. Two weak spots, separated by a few thousand kilometers, together covering a larger area, create a broader zone where satellites are at risk. The total time each satellite spends in elevated radiation goes up. The number of affected orbits goes up. The operational cost goes up. And if the anomaly keeps weakening, if the field strength in the heart of the anomaly drops below some threshold, 20,000 nanoteslas, 15,010, there may come a point where passive shielding is not enough, where you cannot just shut down instruments and wait it out, where satellites have to be designed differently, hardened more aggressively, or where certain orbits become unusable. We are not there yet, but the trend is clear. The anomaly is not shrinking, it is not stabilizing, it is growing, drifting, weakening, and nobody knows when or if it will stop. The South Atlantic Anomaly is not a hole in the sky. It is not a gap in the atmosphere, not a place where air is missing. It is a hole in the magnetic shield, a dent, a place where the field is weaker, where the usual protection against charged particles is diminished, where the inner Van Allen belt sags closer to the surface. The particles are not new. They have always been there, trapped in the magnetosphere, spiraling along field lines, bouncing between the northern and southern mirror points. The anomaly does not create them. It just lets them get closer. And closer matters, because satellites live at altitudes where every kilometer counts. The field above the South Atlantic has been weak before. Sediment cores from the region, analysed in a 2020 study, show periodic weakening over the past 11 million years. The anomaly is not unique, it is recurrent. Something about the structure of the core beneath southern Africa, perhaps linked to the African Large Low Shear Velocity province, that dense, slow region at the core mantle boundary, creates conditions that favour a weak field overhead. The anomaly comes and goes. Sometimes it is associated with excursions, sometimes with reversals, sometimes with neither. It is a symptom but not a diagnosis. Right now, it is both a geophysical curiosity and an operational problem. Scientists study it because it offers a window into the core's dynamics, a visible, measurable consequence of whatever is happening 3,000 kilometers below. Engineers study it because their satellites have to fly through it, and they need to know how bad it will get and how fast. Both groups want the same thing: better models, better forecasts, better understanding. Neither group has enough data yet. The field changes on timescales of years to decades to centuries. Satellites have been measuring it precisely for only a few decades, observatories for less than 2 centuries. That is not enough time to see the full pattern, not enough to distinguish a fluctuation from a trend, a stumble from a fall. So we watch. The Swarm satellites, launched by the European Space Agency in 2013, measure the field from orbit, mapping its three-dimensional structure, tracking its changes month by month. Ground observatories continue their long, patient records. New instruments are deployed, old ones are maintained, the data accumulate, the models improve, slowly, and the field continues to evolve, indifferent to the attention, following whatever dynamics govern a sphere of molten iron spinning and convecting 2,000 kilometers thick, wrapped around a solid core buried beneath a rocky mantle, hidden from every direct probe. The compass still points north, for now. The field is still a dipole mostly. The deviations are growing, but they are still deviations. The majority of the field is still doing what it has done for the past 780,000 years. But the archive, basalt and lava and sediment and ice, observatory records and satellite data, tells us that for now is not the same as forever. The field has failed before, it has recovered before, it has reversed before, and we are living in a moment when it might be starting to do one of those things again, or it might not. The only honest answer is, we are watching, and we do not yet know. The European Space Agency's Swarm mission flies 3 satellites in polar orbit, circling the Earth every 90 minutes, passing over both poles 16 times a day. They were launched together in November of 2013 from Plesetsk Cosmodrome in northwestern Russia, lifted into space aboard a single rocket vehicle. 2 of them, Alpha and Charlie, fly side by side at an altitude of roughly 470 kilometers. The third, Bravo, orbits higher, around 520 kilometers. The formation is deliberate. By flying at different altitudes simultaneously, the the constellation can separate magnetic signals that would otherwise blur together, teasing apart contributions from different layers of the Earth system. Because the magnetic field you measure in orbit is not a single thing, it is a sum, a composite. 5 distinct sources, overlapping, each with its own signature, its own timescale, its own spatial pattern. The largest contribution comes from the core, the geodynamo, the convecting iron 2,000 kilometers deep. That is the signal scientists want. But it is tangled with the magnetic field frozen into the crust, the remnant magnetism of ancient volcanic rock and ore deposits, and with the field induced in seawater as ocean currents move through the Earth's background field. And with currents flowing in the ionosphere, the electrified layer of atmosphere 100 kilometers up, driven by solar radiation and the solar wind, and with the magnetosphere itself, the vast region of space shaped by the interaction between the Earth's field and the charged particles streaming outward from the Sun. Each of these contributions has a different strength, a different geometry, a different rate of change. The core field is strong and slow, varying over years and decades and centuries. The crustal field is weak and static, locked in place since the rock cooled. The ocean field is tiny and irregular, shifting with the tides and currents. The ionospheric field is moderate and fast, changing hour by hour with the Sun's position and activity. The magnetospheric field is large and turbulent, responding to storms in the solar wind, to bursts of particles, to changes in the pressure balance between the Earth's field and the interplanetary medium. SWARM's job is to listen through the noise, to measure the total field at every point along its orbit, and then, using mathematical models and careful filtering, subtract away everything that is not the core. It is a delicate process. The satellites carry instruments sensitive enough to detect changes of a few nanoteslas, a few billionths of a Tesla, roughly 100,000th of the field's total strength. They measure not just the intensity but the direction, the three-dimensional vector, the full shape of the field at every moment. They record their own position with GPS precision. They note the time, the solar activity, the ionospheric conditions, and they send the data down. On the ground, researchers build models. They start with a framework, usually spherical harmonics, the same mathematical language Carl Friedrich Gauss developed in the 1830s, and fit the satellite measurements to it, adjusting thousands of coefficients until the model matches the observations. Then they run the model backward, peeling away the external fields, the ionospheric currents, the magnetospheric distortions. They isolate the core contribution, and they watch how it changes. What they see is not simple. The field is weakening, yes. The global dipole moment, the measure of the field's overall strength, has declined roughly 9% since the 1830s. But the decline is not uniform. Some regions are weakening faster than others, some are strengthening. The South Atlantic Anomaly is the most dramatic example, but it is not the only one. There are changes happening beneath Asia, beneath the Pacific, beneath the poles. The field is not collapsing evenly, it is rearranging. Beneath southern Africa and the South Atlantic, the changes are especially complex. The anomaly is not just a static weak spot. It is drifting westward at roughly 20 kilometers per year, sliding across the surface as the core's circulation patterns shift below. And it is not a single feature anymore. Since around 2014, a second centre of low intensity has been growing southwest of Africa, carving the anomaly into 2 lobes, 2 minima separated by a slight rise in field strength between them. The anomaly is splitting. Chris Finlay, a geophysicist at the Technical University of Denmark and one of the lead researchers on SWARM's magnetic field modelling, has spent years tracking these changes. In interviews and published papers, he has described the South Atlantic region as behaving differently from the rest of the planet. The field there is not simply weakening, it is fragmenting, developing internal structure, responding to forces in the outer core that are not affecting other regions in the same way. He has said that something special is happening beneath southern Africa, something that makes the field weaken more intensely in that region than elsewhere. The question is what? And the answer is incomplete. One possibility is that the anomaly is linked to a feature at the base of the mantle, nearly 3,000 kilometers down, where the rocky mantle meets the liquid outer core. This is the core-mantle boundary, a transition zone where temperatures shift abruptly, where the dynamics of convection change, where the churning iron below meets the sluggish, viscous rock above. In this zone, seismic imaging has revealed 2 enormous structures, each roughly the size of a continent, where seismic waves slow down dramatically. These are the large low shear velocity provinces, or LLSVPs. One sits beneath the Pacific, the other sits beneath Africa. The African LLSVP is thought to be a region of unusually hot, possibly chemically distinct material resting on the core mantle boundary. It affects the flow of heat from the core into the mantle. It may alter the pattern of convection in the outer core directly above it, changing the way molten iron moves, the way magnetic field lines are stretched and twisted, the way the dynamo generates and maintains the field. If the presence of the LLSVP disrupts the core's normal circulation, it might create conditions that favour a weaker field overhead. It might explain why the South Atlantic Anomaly keeps returning, why sediment records show periodic weakening in this region over the past 11 million years, why the field above southern Africa behaves differently than the field above other parts of the planet. But that is a hypothesis, not a confirmed mechanism. The core is not accessible, the boundary is not visible. The connection between a seismic anomaly in the mantle and a magnetic anomaly 3,000 kilometers above it is indirect, inferred, built on models and assumptions and correlations that are suggestive but not conclusive. What is certain is that the anomaly is changing and that Swarm is watching it change. Between 2014 and 2020, the minimum field strength within the anomaly dropped from roughly 24,000 nanoteslas to 22,000. In the 5 years since, it has fallen another few hundred nanoteslas. The rate of decline is not constant. Some years the field weakens faster, some years it stabilizes briefly. The trajectory is noisy, but the overall trend is downward. Anja Strome, the Swarm mission manager at ESA, has described the constellation's data as a new kind of window into the core's behavior, a way to see changes happening now rather than only reading the fossil record of changes that happened millions of years ago. The satellites provide a continuous high-resolution map of the field's evolution, updated every few months as new data come in. Researchers can track the anomaly's westward drift in real time, watch the secondary minimum develop, measure the expansion of the region where field strength falls below a certain threshold. They can compare the current state to models of past excursions and reversals, looking for patterns, for early warning signs, for anything that might indicate where the field is headed next. And they cannot find a reliable forecast. The problem is not a lack of data. The problem is the system itself. The geodynamo is turbulent, non-linear, sensitive to initial conditions in ways that make long-term prediction nearly impossible. Small changes in the flow of molten iron can cascade into large changes in the field. Eddies and vortices interact, merge, split apart. Magnetic field lines are stretched, twisted, reconnected. The system has memory. What happened a century ago still influences what happens today. But it also has chaos. Two nearly identical starting conditions can lead to wildly different outcomes. This is not a matter of needing better instruments or more computing power. It is a fundamental property of the dynamics. So the models can tell you what the field looks like now. They can tell you how it has changed over the past decade, the past century, the past few thousand years if you have enough paleomagnetic data. They can simulate the physics of the dynamo, reproduce the broad features of the field, match the observed decline and the growth of the anomaly. But they cannot tell you whether the decline will continue, whether the field will recover, whether a reversal is beginning. Not with confidence, not with a timeline. Scientists can say that the field is changing. They can say that the changes are significant, that the South Atlantic Anomaly is growing and splitting in ways that are consistent with what models predict might happen during the early stages of an excursion or a reversal. But they can also say that similar changes have happened before without leading to a reversal, that the field has recovered from weaker states, that the current decline, dramatic as it is by human standards, is not yet outside the range of normal variability on geological timescales. The field's intensity right now is still roughly twice as strong as its average over the past few million years. The dipole is weakening, but it is still the dominant component. The non-dipole field, the more complex, smaller-scale structure, is growing, but it has not overtaken the dipole. The magnetic poles are drifting, but they have not wandered into the tropics. The field is stressed, but it is not broken. And there is no clock, no countdown, no schedule that says a reversal is due. The last full reversal, the Brunnes-Matuyama boundary, happened 780,000 years ago. Some studies, using high-precision argon dating of volcanic ash layers in sediment cores, place it at 786,000 years ago. The uncertainty is small compared to the age, but it is there. The reversal itself, the transition from one polarity to the other, took time. Estimates vary. Some records suggest the switch happened in less than a century, a shockingly fast reorganization of the entire field. Others suggest it took several thousand years, a long unstable period with the field weakening, the poles wandering, multiple centers of magnetic intensity appearing and disappearing before the new dipole locked in. Courtney Sprain, a geochronologist at the University of California, Berkeley, has worked on dating reversal boundaries with extraordinary precision, using both argon-argon dating of volcanic rocks and magnetic records from sediment cores. Her work, along with that of Paul Wren at the Berkeley Geochronology Center, has shown that the timing of reversals can be pinned down to within a few thousand years, and in some cases much better. But even with that precision, the picture that emerges is not one of regularity. It is one of irregularity. Reversals do not happen on a schedule, they happen when they happen. Over the past 83 million years, there have been at least 183 reversals. That averages out to one every 450,000 years or so. But averages lie. The intervals between reversals range from tens of thousands of years to millions of years. Some reversals are separated by only 40,000 years, others by more than 1 million. There is no periodicity, no rhythm, no pattern that would allow you to look at the time since the last reversal and predict when the next one will occur. 780,000 years sounds like a long time. It sounds like the field is overdue, like we are living past some invisible deadline. But there is no deadline. The field does not know how long it has been since the last reversal. It does not keep a calendar. The fact that the Brunner's Chron has lasted this long is not evidence that a reversal is imminent. It is just a fact. And there are periods when reversals stopped entirely. The Cretaceous normal superchron is the most striking example. From roughly 121 million years ago to 84 million years ago, a span of 37 million years, the field maintained a single polarity. No reversals, no excursions, just a long, stable interval where the dynamo kept the field pointing in one direction, decade after decade, millennium after millennium, for longer than the entire Cenozoic era. The dinosaurs lived through most of it. Flowering plants diversified under it. The Atlantic continued to widen. Spreading ridges continued to produce new seafloor. Magnetite continued to lock in the field's direction as basalt cooled, but the direction never changed. Why the superchron happened is still debated. Some models suggest it was a period when the core's convection was especially vigorous, when the dynamo was particularly strong and stable, less prone to the fluctuations that lead to reversals. Others suggest it was a time when the core mantle boundary conditions were different, when the pattern of heat flow favoured a stable field. Still others point to the possibility that the superchron ended because something changed at the boundary, perhaps the breakup of a supercontinent, perhaps a change in mantle convection, perhaps the descent of a cold slab of oceanic crust that altered the thermal structure of the lower mantle and indirectly the dynamics of the core. The point is not to explain the superchron. The point is that it existed, that the field can remain stable for tens of millions of years, that there is no rule saying reversals must happen every few 100,000 years, and there are periods when reversals happen far more often. Before the Cretaceous normal superchron during the Jurassic, reversals were frequent. Some intervals saw a reversal every 20,000 to 30,000 years. The field flipped, stabilized briefly, flipped again. The pattern was chaotic by any standard, and then it wasn't. The superchron began, and the chaos stopped. The field's behavior changes over time. Sometimes it is restless, sometimes it is calm. The reasons are not fully understood, but they are thought to be related to changes in the core's thermal and compositional structure, to the way heat is extracted from the core by the mantle, to the balance between the forces driving convection and the forces stabilizing the field. These are not things that change on human timescales. They change on the timescales of plate tectonics, of mantle overturn, of the slow cooling of the Earth's interior. So the fact that the field has been declining for 2 centuries, that the South Atlantic Anomaly has been growing for decades, that the magnetic poles are drifting faster than they were a century ago, none of that tells you a reversal is coming. It tells you the field is changing. That is all. Andreas Nilsson, a geologist at Lund University in Sweden who studies paleomagnetic records of field variability, has pointed out in published work and interviews that anomalies like the one over the South Atlantic are not new, not unprecedented. not necessarily precursors to reversals. They are recurring features, tied to the core's dynamics, linked to the way heat and motion and magnetic field interact deep below the surface. Sometimes they appear during the build-up to an excursion, sometimes during a reversal, sometimes during neither. The anomaly is a symptom of internal change, but it is not a diagnosis. The field can weaken by 90% during a reversal. It can become multipolar, chaotic, unstable, but it can also weaken significantly without reversing. Excursions show that. The Lachance event 41,000 years ago saw the field drop to 5 or 10% of its current strength. It lasted roughly 2,000 years. The poles wandered, the field became a mess, and then it recovered. The dipole reasserted itself. North remained north. So where are we now? The field has declined 9% in 2 centuries. That is measurable, significant, faster than the long-term average rate of change. But it is not unprecedented. Paleomagnetic records show fluctuations of similar or greater magnitude that did not lead to reversals. The South Atlantic Anomaly is expanding and splitting, which is unusual, which is interesting, which might be an early stage of something larger, or it might not be. Bradley Singer, a geologist at the University of Wisconsin-Madison who has studied the timing and dynamics of reversals using volcanic records, has noted that the last reversal was more complex than earlier models suggested, that it began earlier in the core than the surface record initially indicated, that the transition involved multiple stages of field reorganization. His work shows that reversals are not simple flips, they are processes, long, complicated, multi-step processes that unfold over thousands of years, that leave different signatures in different places that are hard to reconstruct even with excellent data. And we are not in a reversal yet. The field is still a dipole. It is weaker than it was, but it is not collapsing. The compass still points north. Satellites still navigate. The magnetosphere still shields the Earth from the solar wind. The South Atlantic Anomaly is a problem for spacecraft, an operational inconvenience, a region where engineers have to design around higher radiation. But it is not a crisis. Not yet. The question is whether not yet will remain true, whether the current changes will accelerate, deepen, lead to something more, or whether the field will stabilize, recover, return to something closer to its long-term average. The archive says both are possible. The models say both are possible. The data say the field is changing, but they do not say where the change is going. We are listening to the core from space, measuring its output with instruments sensitive to shifts smaller than the field of a refrigerator magnet, tracking changes month by month, year by year. And the core is not speaking clearly. It is not announcing its intentions. It is just doing what it does, convecting, generating magnetic field, responding to forces and flows and instabilities that are hidden from us, that we can only infer from the field they produce. So we watch, and we wait, and we accept that the planet does not follow a schedule, that 780,000 years since the last reversal is not a deadline, that the field's current behavior might be the beginning of something, or might be nothing more than a fluctuation in a system that has been fluctuating for billions of years. The answer will come, but it will come slowly, one measurement at a time, 1 year at a time, over a span of time longer than any satellite mission, longer than any career, longer than any single generation of instruments or scientists. And until it does, the only honest answer remains the same. Something significant is happening, but its destination is unknown. The field is changing. That much is settled. What that means for us, for a civilization built in an era when compasses pointed reliably northward, when satellites orbited in predictable radiation zones, when power grids hummed beneath skies shielded by an invisible magnetosphere, is a question we have only just begun to face. Because we have never done this before. No technological society has ever lived through a geomagnetic reversal. No technological society has ever lived through a deep excursion. We have radar and GPS and transcontinental power transmission and orbital infrastructure, and all of it was designed and deployed under the assumption that the magnetic field would remain more or less as it has been for the past few thousand years. Stable enough, strong enough, predictable enough. That assumption is now under examination. Start with the simplest question. What does a weaker magnetic field actually do? The field itself is not a physical barrier. It does not stop anything by collision. It deflects. Charged particles, protons, electrons, solar wind plasma, cosmic rays, spiral along magnetic field lines, are bent away from Earth are funneled toward the poles where the field lines converge and dive into the atmosphere, producing auroras. The stronger the field, the more effectively this deflection works. The weaker the field, the less protection it offers. At the surface, under normal conditions, the atmosphere itself absorbs most of what gets through. The field and the atmosphere work together, but at altitude the atmosphere thins, and in space it vanishes entirely. So the stakes rise as you climb. Consider aviation. A commercial airliner at cruising altitude, 30 to 40,000 feet, is above roughly 70% of the atmosphere's mass. The air is thin enough that cosmic radiation, which is mostly absorbed lower down, begins to reach the aircraft. Pilots and flight attendants are classified as radiation workers in the European Union under Council Directive 96/29 Euratom, because their cumulative exposure over a career can exceed that of some nuclear power plant employees. The radiation comes from galactic cosmic rays, high-energy particles originating outside the solar system, and from solar energetic particles during solar storms. Both are modulated by the magnetic field. Weaken the field, and more radiation reaches cruising altitude. Polar routes are the worst. The magnetic field lines converge at the poles, and the shielding there is already weaker than at the equator. Flights between North America and Asia, or between Europe and the Pacific, often pass near the Arctic. During a solar storm, a coronal mass ejection that sends a surge of charged particles toward Earth, airlines have been known to reroute flights to lower latitudes, trading fuel efficiency for reduced radiation exposure. In a world where the field is significantly weaker, those diversions might become routine, or the acceptable cumulative dose for air crews might be reached faster, limiting how much they can fly. The calculations are not simple. Dose depends on altitude, latitude, solar activity, and the strength and geometry of the magnetic field at the time of the flight. Models exist, but they rely on knowing what the field looks like. If the field becomes multipolar during a reversal, if the shielding over mid-latitudes weakens while new poles wander across the tropics, the radiation maps airlines use would have to be redrawn constantly, and there would be a lag. Satellite measurements take time to process. Field models take time to update. Routes would be planned using outdated assumptions, and the dose received might not match the dose predicted. None of this is catastrophic. It is a problem of margins. Safety margins, regulatory margins, operational margins, the kind of problem that does not make headlines until something fails. Now move higher, low Earth orbit, where the International Space Station circles, where the Hubble Space Telescope drifts, where constellations of Earth observation satellites and communications relays and weather monitors maintain their slow procession. Here, the atmosphere is gone. The only shielding is the magnetic field, and in some regions, like the South Atlantic Anomaly, that shielding is already compromised. Satellites passing through the anomaly are exposed to higher fluxes of energetic protons trapped in the inner Van Allen belt. These particles can penetrate spacecraft electronics, flip bits in memory, degrade solar panels, damage sensors. Operators respond by shutting down sensitive instruments during transits, putting the spacecraft into a safe mode where only essential systems remain active. For the International Space Station, that means astronauts avoid extravehicular activities when passing through the anomaly. For Hubble, it means the telescope stops taking images. For Earth observation missions, it means gaps in coverage, moments of blindness over South America and the South Atlantic. This is manageable, but it is costly. Every shutdown is lost data. Every bit flip requires error correction. Every degraded component shortens mission lifetime. And the anomaly is growing. It has expanded westward, split into two lobes, deepened. More satellites are affected. Transit times are longer. The operational cost rises. If the field continues to weaken, if the anomaly continues to expand, the affected region grows. Eventually it might not be a regional problem. Eventually it might be a global one. Satellites in polar orbit cross high latitudes where the field is naturally weaker. Satellites in equatorial orbit might find themselves exposed as mid-latitude shielding degrades. And if the field becomes multipolar during a reversal, the radiation environment in low Earth orbit could become so hostile that some missions simply cannot operate. Not because the spacecraft would be destroyed instantly, but because they would accumulate damage faster than they could be repaired or replaced. There is also the question of drag. The magnetic field influences the shape and behavior of the upper atmosphere. When the field interacts with the solar wind, it compresses on the day side and stretches into a long tail on the night side. The boundary between the magnetosphere and space, the magnetopause, fluctuates. During geomagnetic storms, energy from the solar wind is dumped into the upper atmosphere, heating it, causing it to expand. Satellites in low orbit experience increased drag. Their orbits decay faster. They require more frequent boosts to maintain altitude. In a weaker field or a disordered one, the magnetopause would sit closer to Earth. The upper atmosphere would be more exposed to solar wind heating. Storms might become more intense or more frequent, or both. Orbital decay rates would rise. The operational lifetime of satellites would shorten. Orbital debris, already a growing problem, would decay faster, which sounds like a benefit, except that debris in decaying orbits sweeps through a wider range of altitudes, increasing collision risk before it finally burns up. None of this is speculation. It is extrapolation from known physics, from measured effects during geomagnetic storms, from the behavior of the system under stress. A reversal would be a very long, very slow geomagnetic storm, and we would have to live with it for thousands of years. Then there is the question of navigation. GPS, GLONASS, Galileo, Beidou, every satellite navigation system in operation depends on precise timing and orbital knowledge. A receiver on the ground calculates its position by measuring the time delay of signals from multiple satellites, each broadcasting its location and the exact time the signal was sent. The accuracy of that position depends on the accuracy of those orbital predictions. But the satellite's orbits are influenced by gravitational perturbations, solar radiation pressure, atmospheric drag, and the magnetic field. If the field changes, if it weakens, if it becomes multipolar, if its geometry shifts, the models that predict satellite orbits have to be updated. And if the field is changing rapidly, those updates lag. The predicted orbit and the true orbit diverge. Position accuracy degrades. For most civilian users, a few meters of error is acceptable. For precision agriculture, surveying, autonomous vehicles, military targeting, it is not. And it is not just position. Timing matters. Financial transactions are time-stamped with GPS time. Power grids synchronize using GPS. Telecommunications networks rely on it. If GPS accuracy degrades, those systems either have to accept the degradation or switch to backup methods, which are more expensive, less convenient, harder to deploy globally. And GPS is not the only thing that depends on the field. Radio communication at certain frequencies is affected by the ionosphere, the layer of the atmosphere where solar ultraviolet radiation ionizes atoms, creating a layer of free electrons that can reflect radio waves. The ionosphere's behavior is influenced by solar activity and by the magnetic field. Change the field and you change the ionosphere. Propagation paths shift, signal strength changes, communication links that worked reliably might not. Again, this is not a catastrophe. It is 1,000 small degradations, each of which requires adaptation, redesign, additional cost. A civilization can absorb that. But it is worth noticing that the absorption is not free. Now consider the power grid. Long-distance transmission lines are excellent antennas. When the magnetic field changes rapidly during a geomagnetic storm, it induces electric currents in the ground, telluric currents, which couple into the transmission lines and appear as quasi-DC offsets superimposed on the AC power signal. Transformers are not designed to handle DC. The offset causes the transformer core to saturate, which increases losses, generates heat, produces harmonics, and in extreme cases can cause permanent damage. The most famous example is the March 1989 geomagnetic storm that knocked out power to 6 million people in Quebec for 9 hours. The storm was triggered by a coronal mass ejection, a massive eruption of plasma and magnetic field from the sun. When it reached Earth, it compressed the magnetosphere and drove currents through the ionosphere, which in turn induced currents in the ground. Transformers at the Hydro-Quebec facility failed. The grid collapsed. That was a storm, a single event lasting hours. A geomagnetic reversal is not a storm. It is a sustained weakening of the field over thousands of years. But during that weakening, the field becomes more vulnerable to storms. The shielding that normally deflects solar wind becomes less effective. Coronal mass ejections that would have been minor events under a strong dipole field can become major events under a weak multipolar one. And coronal mass ejections are not rare. The sun produces them regularly, especially during solar maximum. Most miss Earth. Some graze the magnetosphere. A few hit directly. In a strong magnetic field, even a direct hit can be absorbed. In a weak field, the same hit can be devastating. There is an important distinction here that is often confused. A geomagnetic reversal and a solar storm are not the same thing. A reversal is slow, internal, driven by changes in the dynamo deep in the outer core. A coronal mass ejection is fast, external, driven by magnetic instabilities in the Sun's corona. They are separate phenomena, but they interact. A weak field makes the Earth more vulnerable to solar weather, and solar weather is not optional. The Sun does what the Sun does, and we are in range. So the stakes are real. They are not existential. Life will not end if the field reverses, but they are significant. We have built a world that depends on satellites, on GPS, on power grids, on radio communication, on the assumption that the space around Earth is predictable, and that the magnetic field will continue to provide the shielding it has provided for as long as we have been measuring it. If that assumption breaks, the world does not end. But it becomes more expensive, more fragile, harder to manage, and we have no experience with this. We have never had to redesign orbital infrastructure for a multipolar field. We have never had to reroute global air traffic under sustained radiation exposure. We have never had to harden a planetary power grid against decades or centuries of elevated geomagnetic storm risk. Other civilizations have, though. Not technological civilizations, those are new, but human ones. Anatomically modern humans, Neanderthals, Denisovans. They lived through the La Chance excursion, 41,000 years ago, when the field dropped to 5% of its current strength, and the poles wandered across the equator. The evidence comes from lava flows. Bonhomet and Babkin, working in the 1960s near Clermont-Ferrand in France, found volcanic rocks at La Chaume and Olby, whose magnetization pointed south instead of north. The flows were young, Holocene, they thought at first. But further dating pushed the age back. 40,000 years, roughly. More evidence followed. Sediment cores from the North Atlantic, speleothems from the Americas, and in the early 21st century, tree rings from ancient kauri logs preserved in New Zealand swamps. The Ngawa log, a section of kauri trunk that lived through the excursion, recorded the event in the carbon-14 content of its growth rings. When the magnetic field weakened, more cosmic rays reached the upper atmosphere, producing more carbon-14. The spike is visible. The timing is precise. 42,000 years ago, give or take a few centuries, the magnetic poles tilted more than 75 degrees from the geographic axis. The field strength dropped by 90 to 95%. The transition into the reverse state took roughly 250 years. The reversed field persisted for about 440 years. Recovery took thousands of years, at least 10,000 before the field returned fully to its current configuration. For 4 centuries, the Earth had almost no magnetic shielding. Cosmic rays and solar wind poured into the atmosphere at rates far higher than today. Ozone was depleted. Surface ultraviolet radiation increased. Atmospheric chemistry shifted. Auroras, normally confined to high latitudes, appeared near the equator. The sky would have glowed green and red on nights that should have been dark, and humans were there. Homo sapiens had spread across Africa, the Middle East, Asia, Australia. Neanderthals still inhabited Europe and Western Asia. Denisovans persisted in the East. They were hunter-gatherers, adapted to a wide range of environments, skilled at making tools, at managing fire, at tracking game and reading landscapes. What did they experience? The field itself is invisible. They would not have noticed it weakening directly, but they might have noticed the consequences. The auroras, certainly. Strange lights in the sky, rippling curtains of colour, would have been visible far more often and far farther south than anyone living had ever seen. If oral traditions carried memory across generations, elders might have spoken of a time when the sky was normal. But 40 years is enough to forget. 400 years is enough that the strangeness becomes the norm. Radiation exposure would have increased. At the surface, under a full atmosphere, the increase is modest, but it is real. Ultraviolet flux would have risen if the ozone layer thinned. That much is consistent with models of what happens when cosmic rays flood the upper atmosphere. Whether that was enough to drive behavioral changes, increased use of caves for shelter, more reliance on clothing, application of ochre as a sunscreen, is harder to say. There is evidence that ochre use increased among Homo sapiens in Africa and Europe during this period. Red and yellow ochre, ground and mixed with fat, has some UV blocking properties. It also has symbolic and ritual uses. Disentangling practical response from cultural practice is difficult, and the evidence does not support strong claims. It is suggestive, it is interesting, it is not proof. The claim that has generated the most controversy is whether the Lachamps excursion caused the extinction of Neanderthals. A 2021 paper published in Science by Alan Cooper and Chris Turney argued that the environmental disruption from the weakened field, ozone depletion, increased UV, shifting wind patterns, possible effects on climate, created stress that contributed to Neanderthal decline. They called the event the Adams event, a reference to Douglas Adams and the number 42. The paper made headlines. It also drew criticism. Other researchers pointed out that Neanderthal populations had been declining for tens of thousands of years before Lachamps, that their disappearance was gradual and regionally variable, that previous excursions, like the Blake event around 120,000 years ago, had not caused similar extinctions, and that Homo sapiens, who lived through the same event, not only survived but thrived. The correlation between the excursion and the extinction was weak. The proposed mechanism was speculative. The paper's claims outran its evidence. The truth is probably more modest. The Lachamps excursion was real. The field weakened dramatically. The environmental effects were real. Radiation increased. Auroras expanded. The ozone layer was disturbed. Humans and Neanderthals lived through it, and life continued. No mass extinction. No collapse of ecosystems. The biosphere bent and then recovered. That is worth holding on to, because it shows that even a 95% reduction in field strength sustained for centuries is survivable. Not comfortable, perhaps, not without consequences, but survivable. There are limits, though. The Lachamps excursion occurred during the last ice age. Human populations were smaller, more dispersed, less reliant on complex infrastructure. A group of hunter-gatherers displaced by shifting resources can migrate. A city cannot. A power grid cannot. A satellite constellation cannot. And there is the question of what happens when weakened shielding meets a major solar storm. The sun was quieter during the Lachamps event. At least that is what the carbon-14 record suggests. Solar activity was lower. Coronal mass ejections were less frequent. If a large ejection had occurred during the weakest phase of the excursion, when the field was at 5% and multipolar, the radiation environment at the surface would have been significantly worse. Perhaps enough to matter biologically, perhaps not. We do not have data from such an event. So the Lachamps excursion is both a reassurance and a warning. Life survived. Humans survived. But the humans who survived were not dependent on satellites, or power grids, or GPS. They adapted by moving, by sheltering, by changing their behavior in ways that left faint marks in the archaeological record. We would have to adapt differently, and that brings us back to the present, to the South Atlantic Anomaly, the 9% decline, the westward drift, the splitting lobes, the satellite shutdowns, the questions nobody can answer with certainty. Is this a reversal beginning? The paleomagnetic record shows that not every weakening leads to a reversal. Excursions are more common than reversals. The field can drop, wander, and recover without flipping. It has done so many times, but reversals do happen, and they start with weakening. Is the South Atlantic Anomaly a precursor or a recurring feature? Recent research from the University of Liverpool, led by Yael Engbers, analysed volcanic rocks from St Helena, an island in the middle of the South Atlantic. The rocks record magnetic field behaviour over millions of years, and they show that the anomaly, or something very like it, has appeared before, multiple times. The region above the South Atlantic has been weak periodically for at least 11 million years, linked possibly to structures at the core mantle boundary beneath southern Africa. Engbers concluded that the anomaly is a recurring feature of the geodynamo, not necessarily a sign of an impending reversal. But recurring and precursor are not mutually exclusive. The anomaly can be a recurring feature, and still, on some occasions, be part of a reversal process. The question is which this is. The models do not help. Computer simulations of the geodynamo can generate reversals, but they cannot predict them. The system is chaotic. Small changes in initial conditions lead to wildly different outcomes. Some runs produce a reversal, some produce an excursion, some produce a weakening that stabilizes and recovers. There is no periodicity, no clock, no reliable precursor signal. Recent studies of past reversals have found that the process is longer and more complex than once thought. The Brunnes-Matuyama reversal 780,000 years ago may have begun earlier in the core than the surface record shows. The transition involved multiple stages, with the field weakening, reorganizing, weakening again before finally flipping. The duration? Estimates range from a few thousand years to tens of thousands, depending on how you define the beginning and end. Some researchers argue that certain reversals took even longer, up to 70,000 years in one case, based on marine sediment records. Yuji Yamamoto, a paleomagnetist at Kochi University in Japan, expressed astonishment at findings of such prolonged reversal processes, noting they challenge conventional understanding. The reversals we thought we understood turn out to be more complicated than the data initially suggested, and that means forecasting the current field's trajectory is impossible. The decline since the 1830s is measurable. The South Atlantic Anomaly is measurable. But whether the decline will continue, accelerate, stabilize, or reverse is not something the data can tell us. Not yet. Maybe not for decades. Maybe not for centuries. Carl Friedrich Gauss made the first absolute measurements of the magnetic field's intensity in 1832, establishing the baseline we still reference. Nearly 2 centuries of careful observation, a global network of magnetic observatories, satellite missions measuring the field with exquisite precision, and still the answer to the most consequential question is, we do not know. The geodynamo is hidden beneath 3,000 kilometers of rock. We cannot see it. We can only measure its output, and that output is changing, but the change so far is ambiguous. It could be noise, it could be signal. It could be the beginning of something profound, or it could be a fluctuation that will fade. The only way to know is to wait, and while we wait, we make decisions. Satellite operators decide whether to harden new spacecraft against higher radiation. Power companies decide whether to invest in transformer protection. Aviation regulators decide whether to adjust dose limits for air crews. Governments decide whether to fund research into magnetic field forecasting, or to wait for certainty that will not arrive in time to matter. So the watching continues. The International Space Station completes one orbit every 92 minutes, 16 sunrises, 16 sunsets, every day. And twice each day, sometimes 3 times depending on orbital geometry, the station crosses the South Atlantic Anomaly. The crew does not feel it. There is no sensation. The hull does not vibrate. The air does not change. But the instruments know. The dosimeters tick upward. Radiation monitors log the passage. Sensitive detectors are powered down before entry, reactivated after exit. The anomaly is invisible to human senses but legible to electronics, a zone of vulnerability written into every orbital mission plan. Satellites crossing the anomaly experience higher rates of bit flips, single event upsets, in the language of spacecraft engineers, where a charged particle strikes a memory cell and changes a 0 to a 1 or a 1 to a 0. Most are caught by error correction codes. Some are not. A satellite's onboard computer might reboot. A star tracker might lose orientation. An imaging sensor might record a streak of noise across an otherwise clear frame. These are routine now. Operators plan for them. Redundant systems compensate, but the frequency is increasing. The anomaly is growing, and the affected zone is wider each year than the year before. The Hubble Space Telescope, orbiting at 550 kilometers, shuts down its science instruments during every South Atlantic passage. It has done so since launch. The procedure is automated. As the telescope enters the boundary, defined not by geography but by radiation intensity, commands execute, detectors go dark, and Hubble drifts through in safe mode, waiting for the far edge. Then the instruments wake again, resume observation, continue the work. Hubble crosses the anomaly 10 times a day, roughly 6,000 times a year. The telescope has made that crossing more than 200,000 times since 1990. Each one costs observation time. Each one is a small tax levied by a weakening field. The swarm satellites, lower and faster, cross more often. Their mission is to measure the field itself so they do not shut down. They record. They map the contours of the anomaly in exquisite detail. The depth of the minimum, the shape of the boundary, the drift westward, the splitting into 2 lobes. The data flow to ground stations are processed, modelled, archived, and every few months the models are updated to reflect the changes. The anomaly is not static. It moves, it evolves, and the satellites, crossing it again and again, document every shift. Imagine the view from one of those satellites, not what the instruments see, magnetic field vectors, radiation counts, particle flux, but the view a human passenger would have if such a thing were possible. You're in low Earth orbit, travelling at 28,000 kilometers per hour, fast enough that the horizon visibly curves away beneath you. You pass over the bright lights of São Paulo, then the darkness of the Atlantic, then the southern tip of Africa. The Earth below is turning and you are falling around it, tracing the same path over and over with slight variation each orbit as the planet rotates beneath you. Somewhere over the South Atlantic, the invisible threshold is crossed. You would not see it. There is no line, no change in the colour of the ocean, no shimmer in the atmosphere. But the instruments register it. The radiation environment shifts. The magnetic field strength, which everywhere else on the planet holds the inner Van Allen belt at bay, here weakens enough that the belt sags inward, and particles that would ordinarily remain trapped hundreds of kilometers higher now reach down to orbital altitude. The spacecraft is inside the anomaly. It will remain there for 8 minutes, maybe 10, depending on trajectory and the anomaly's current extent. Then it will exit the far side and the field will strengthen again, and the passage will be logged, and the orbit will continue. 16 orbits a day, 30 passages through the anomaly each week, 1,500 passages a year. The satellite does not tire, it does not grow anxious. It measures, records, transmits. But the data it sends describe a planet whose magnetic environment is not what it was. 3,000 kilometers below the satellite, beneath the ocean, beneath the crust, beneath the mantle, the outer core continues its restless motion. Liquid iron, hotter than the surface of the sun, convecting in vast plumes and eddies, driven by the cooling of the inner core and the rotation of the planet. The flow is turbulent, chaotic, sensitive to conditions at the core mantle boundary and to the history of the flow itself. It is a system with no equilibrium, no preferred state. The field it generates is an emergent property, a side effect of motion, and the motion is never still. The field reaches outward from the core, threads through the mantle, which is an insulator and does not participate, then emerges into the crust and atmosphere and space beyond. It extends tens of thousands of kilometers into the solar wind, forming the magnetosphere, a bubble that shields the planet from the particle streams blown outward by the sun. But the field is not uniform. It has structure, loops and whirls and weak spots. And the South Atlantic Anomaly is one of those weak spots, a place where the field is thinner, where the shield does not hold as well, where the radiation environment resembles what it would be everywhere if the field were absent. And the field has been absent, not recently, not in human memory, but it has happened. The basalt stripes prove it. Those stripes, locked into the seafloor along the mid-ocean ridges, are a record older and more complete than any written history. They are the planet's own archive. Each stripe represents a period when the field pointed one way or the other, north or south, and the pattern repeats symmetrically on either side of the ridge as the seafloor spreads. The stripes are not uniform in width. Some are broad, representing millions of years of stable polarity. Some are narrow, representing brief intervals. And between the stripes, in the transitions, the field was weak, multipolar, chaotic. The Brunnes-Matuyama boundary, the most recent reversal, is recorded in those stripes. It is also recorded in sediment cores, in volcanic rock, in ice. The transition, 780,000 years ago, took thousands of years. During that time, the field weakened, the poles wandered, magnetic north was not north. Compasses, had they existed, would have pointed in directions that changed year by year, decade by decade. The magnetosphere thinned, cosmic radiation increased, auroras appeared at latitudes where they normally do not, and then, slowly, the field reorganized, strengthened, and settled into the opposite polarity. South became north, north became south, and the planet continued. It has happened more than 150 times in the last 70 million years. The pattern is irregular. Sometimes reversals are separated by a few 100,000 years, sometimes by tens of millions. There is no cycle, no rhythm. The geodynamo operates on its own schedule, which is to say it has no schedule. It is driven by thermodynamics and fluid dynamics, and the interplay of rotation and convection, and those forces do not produce regularity. They produce complexity, variability, reversals when conditions align in some way we do not fully understand, stability when they do not. And between the reversals there are excursions, shorter events. The field weakens dramatically. The poles wander far from their usual positions, but the field does not complete a reversal. It stumbles, recovers, resumes. The Lachance excursion, 42,000 years ago, was one such event. The field dropped to a small fraction of its current strength. It lasted a few centuries at its weakest point, then recovered over the next 2 millennia. Humans lived through it. No extinction, no collapse, but also no satellites, no power grids, no infrastructure depending on precise navigation or protection from radiation. Now, for the first time, a technological civilization is watching the field as it changes in real time. The 9% decline since the 1830s, the drift of the North Magnetic Pole, accelerating from 15 kilometers a year to more than 50. The South Atlantic Anomaly, expanding and splitting. These are measurable changes. They are not hypothetical. They are happening. But what they mean is not clear. Are they the early stages of a reversal, an excursion, a fluctuation that will reverse itself? The data accumulated so far, 2 centuries of ground measurements, a few decades of satellite data, are not enough to answer. The geodynamo operates on timescales of thousands to millions of years. 2 centuries is an instant. It is not enough to see the shape of the trajectory. It is barely enough to confirm that there is a trajectory. Computer models of the geodynamo can reproduce the field's large-scale structure. They can generate reversals in simulation, but they cannot predict when a reversal will occur because the system is chaotic. Small differences in starting conditions lead to completely different outcomes. A model run might produce a stable field for millions of simulated years. Another run, with nearly identical starting conditions, might produce a reversal in a few thousand. The sensitivity is extreme, and the models are approximations. They simplify the physics, they run at lower resolution than the real core. They cannot capture every eddy, every instability, every feedback. They are useful for understanding the kinds of behavior the geodynamo can produce, but they are not forecasts, so the scientists watch. They refine the models, they collect more data, they look for precursor signals, patterns in the field's behavior that might indicate a reversal is beginning. So far, no reliable precursor has been found. Some weakening events lead to reversals, some do not. The South Atlantic Anomaly has appeared before, over millions of years, sometimes associated with excursions or reversals, sometimes not. It is a recurring feature, yes, but that does not mean it is benign. Recurring features can still be precursors. The question is whether this instance of the anomaly, now, is simply another recurrence, or whether it is part of a deeper process. The honest answer, the only answer supported by the data, is that we do not know. And so decisions are made without certainty. Satellite designers add radiation shielding, at the cost of weight and complexity. Power grid operators install monitoring equipment to detect geomagnetically induced currents, knowing that a severe space weather event could damage transformers, but not knowing whether such events will become more frequent as the field weakens. Aviation authorities track cosmic radiation exposure for flight crews, especially those flying polar routes where the field is already weaker. GPS system operators update the world magnetic model every 5 years, sometimes more often when the field changes faster than expected, ensuring that navigation systems account for the shifting field. Space agencies plan missions with the South Atlantic Anomaly in mind, designing orbits that minimize exposure or accepting the operational cost of shutting down instruments during passage. These are adaptive measures, responses to a changing environment. They do not require knowing whether a reversal is coming. They require only acknowledging that the field is not static, that it is weaker in some places than others, and that those places are growing. But there are limits to adaptation. If the field continues to weaken, if the South Atlantic Anomaly expands further, if a reversal or deep excursion actually begins, the consequences will scale beyond what incremental measures can address. The magnetosphere would thin globally, low Earth orbit would become a harsher environment, radiation exposure on the ground would increase, especially at high latitudes. Satellite lifetimes would shorten, power grids would face more frequent disturbances, GPS accuracy would degrade, radio communication would be disrupted more often. These are not speculative risks. They are the known consequences of a weakened magnetic field, observed in the paleoclimate record and inferred from models of the magnetosphere. How severe those consequences would be depends on how weak the field becomes and how long it stays weak. A brief excursion, lasting a few centuries, would be disruptive but survivable. A full reversal, lasting tens of thousands of years, with the field at a fraction of its current strength for much of that time, would be a different matter. Humanity would endure. There is no evidence that previous reversals caused mass extinctions, but the infrastructure of the modern world was not designed for that environment. And yet the stripes on the seafloor, the record locked in basalt, suggest that reversals are not catastrophes. They are transitions. The planet has reversed its field more than 150 times, and life continued. The biosphere adapted. Species that depend on magnetic navigation, migratory birds, sea turtles, certain fish, navigated through the transitions, or their populations fluctuated and recovered, or they evolved other strategies. The geologic record does not show mass die-offs correlated with reversals. It shows continuity. What it does not show is a technological civilization crossing a reversal. That is new. We are the first to watch the field change with instruments sensitive enough to measure it in real time. The first to depend on satellites orbiting in the radiation belts. The first to navigate using magnetic models updated faster than the field itself shifts. The first to generate and transmit electricity across continental distances through grids vulnerable to geomagnetic induction. The first to need to know, years or decades in advance, what the field will do. And the field is not telling us. Not yet. The swarm satellites continue their orbits. Ground observatories continue their measurements. Researchers continue to refine models, drill new cores, analyze volcanic rocks for their magnetic fingerprints. The data accumulate. The picture sharpens slowly. But the central question, whether the current changes are the beginning of a reversal, an excursion, or a fluctuation, that question remains open. It will not remain open forever. If the field continues to weaken, if the South Atlantic Anomaly continues to grow, if the decline accelerates, then at some point the answer will become clear. Not through prediction, but through observation. The field will tell us what it is doing by doing it. And by the time the answer is unambiguous, the transition will already be underway. That is the difficulty. The geodynamo does not give advance warning. It does not signal its intentions. It simply changes, and we measure the change, and we respond as best we can. The seafloor stripes offer one kind of reassurance. They show that the planet has been through this before, many times. The field has weakened, reversed, strengthened again. The process is not smooth, not quick, but it is survivable. The stripes are symmetric, orderly in their pattern, evidence that the geodynamo, for all its chaos, eventually stabilizes. The field always comes back. But the stripes also offer a warning. They show that the field we depend on, the field that has pointed north for 780,000 years, the field that has been strong and stable for all of recorded history, is not permanent. It is a phase, a temporary state, and phases end. The South Atlantic Anomaly is growing. The field is weakening. The core is changing. These are facts. What comes next is not. Perhaps the decline will slow. The anomaly will stabilize. The field will recover, as it has after previous excursions. In a century, the 9% loss will be remembered as a fluctuation, a brief perturbation in an otherwise stable epoch. Magnetic north will continue to drift as it always has, but the field will remain strong. The magnetosphere will hold, and the satellites will cross the anomaly with no more difficulty than they do now. Or perhaps the decline will continue. The anomaly will deepen, split further, drift westward until it sits over South America, then North America, affecting more satellites, more orbits, more infrastructure. The field will weaken further, 10%, 20, 30. The magnetic poles will begin to wander more erratically. The dipole will become less dominant. The field will enter a transitional state, multipolar and unstable, with no clear north or south. Navigation systems will require constant updates, faster than they can be deployed. Radiation levels in low Earth orbit will rise beyond what current shielding can handle. Some satellites will fail, some will be abandoned. The cost of operating in space will increase. Power grids will experience more frequent disturbances. Auroras will appear at mid-latitudes, beautiful and strange, a visible sign of a thinning magnetosphere. And over thousands of years the field will reorganize. It will pass through a phase of extreme weakness, perhaps dropping to 10% of its current strength, perhaps lower. During that time, cosmic radiation will increase. The atmosphere will still provide significant shielding, but high-altitude regions and polar latitudes will experience higher exposure. The biosphere will adapt, as it has before. Technology will adapt more slowly at greater cost. Eventually the field will strengthen again. The core will settle into a new configuration. The dipole will re-establish with the opposite polarity. South will be north, north will be south. Compasses will point the other way, and the planet will continue. This has happened before, it will happen again. The question is only when. The researchers who study the geomagnetic field are careful with their language. They do not say a reversal is imminent. They do not say it is impossible. They say the field is changing, and they describe the changes with precision, and they state clearly what is known and what is not. The decline is real. The South Atlantic Anomaly is real. The drift of the magnetic poles is real. Whether these changes are the beginning of a reversal is not known. The data are not sufficient. The models are not predictive. The system is too complex, too chaotic, too sensitive to initial conditions. What is known is that the field has always been dynamic. It has never been static. The stability of the Brunner's Chron, 780,000 years with the same polarity, is long by human standards but unremarkable by geologic standards. The Matuyama Chron, before it, lasted 2.5 million years. The Gauss Chron, before that, 600,000. These are phases. They end, and when they end, the transitions are neither smooth nor quick. They are messy, prolonged, disruptive, and we are living in one of those phases. The Brunner's Chron, the current normal polarity interval. It has lasted longer than the human species has existed, longer than the genus Homo, longer than stone tools. For all of human history, magnetic north has pointed north. Every compass, every navigation system, every map has assumed it. The field has been our invisible ally, deflecting solar wind, trapping radiation, making the surface of the planet habitable in ways we rarely consider. But it will not last forever. It is already changing, and the changes are accelerating. The basalt on the seafloor does not care. It records whatever polarity the field holds at the moment the rock cools. Normal or reversed, strong or weak, the magnetite crystals align, lock into place, and remain. 50 million years from now, a researcher, human or otherwise, could drill a core from the South Atlantic seafloor and read the record. They would see the Brunner's Chron, the long stripe of normal polarity. They would see the Matuyama before it, and somewhere in between they would see the boundary, the transition, the reversal. Whether that reversal is the one happening now, or one that happens in another 100,000 years, or another million, the core would not say. It would only show that the reversal happened, that the field flipped, that the planet continued. That is the longest view. The view from deep time where individual human lives are invisible, where civilizations are brief experiments, where even species are transient. From that view, the magnetic field is always changing. Reversals are routine. The field is weak half the time, strong the other half, and the transitions are just transitions, nothing more. But we do not live in deep time. We live in decades. We build infrastructure that must last years, satellites that must survive their design lifetimes, power grids that must operate reliably every day. We navigate by instruments that assume the field will not change too quickly. We plan missions, launch spacecraft, design systems around a field that we hope will remain predictable. And the field is not cooperating. It is doing what it has always done. It is responding to forces in the core that we can only infer. It is evolving, drifting, weakening in some places, strengthening in others, following dynamics that are non-linear, chaotic, and beyond our ability to predict with the data we have. It is behaving like a system with no memory, no obligation to the past, no consideration for the infrastructure we have built assuming it would stay the same. The task, then, is not to predict the field. It is to observe it, to measure it as precisely as we can, with as many instruments as we can deploy, for as long as we can sustain the effort, to build models that improve our understanding, even if they cannot forecast. To prepare for a range of possible futures, knowing that we will not know which future we are in until we are already living it. This is not satisfying. It does not provide certainty. It does not allow for long-term planning with confidence. But it is the only honest response to a system that does not reveal its intentions in advance. The satellites will continue to cross the South Atlantic Anomaly. The instruments will continue to shut down during passage, then wake again on the far side. The data will continue to accumulate. The models will continue to improve, and eventually the trajectory of the field will become clear. Not because we predicted it, but because we watched it happen. That is the work of this century, to watch, to measure, to respond, to acknowledge that the planet beneath us is not inert, not finished, not stable. It is dynamic. It is alive in the geologic sense, driven by heat and motion and forces that operate on scales we're only beginning to comprehend. The magnetic field is one expression of that motion, a side effect of the core's restless convection, and like all things driven by chaos, it changes. The stripes on the seafloor are both warning and reassurance. They are a record of instability, yes, a history of reversals, transitions, phases where the field was weak and disorganized, but they are also a record of recovery. The field always comes back, it reorganizes. I